Only two more layers to go, transport and application. So in this video, I will provide you an overview of the transport layer. But first, do you remember what the transport layer does? Before we get into the role of the transport layer, here is a quick recap. We have reached quite a few milestones. We started out with a simple two-node network over a point-to-point link, and then we scaled it up to tens of nodes operating in a local area, and then we extended it to cover thousands of nodes, and then we interconnected heterogeneous networks to span millions of nodes. Right now, we know how to handle host-to-host delivery. You give a packet with the correct destination IP address. We know how to send it to the right destination. Basically, what happens is that the network layer determines which next hop to take along the path, and then it uses the services of the link layer to actually deliver the packet to the next hop, which in turn takes the services of the physical layer to convert the bits to signals to deliver the packet. But host-to-host delivery alone is not enough, because applications run as processes and a given host can have many processes, and we need to provide a method for process-to-process communication. So this is the role of the transport layer. As mentioned, a given host can run many applications. For example, on your own machine, if you run the top command in Unix, it will list a whole range of processes. By the way, not all of them are networking processes, but some processes you will see will be your web browsing processor, your email process, and then if you're running an SSH session, there'll be an SSH process, so on and so forth. So the transport layer's job is to provide logical communication between these processes. Let me emphasize on this word logical. What do I mean by this logical communication? Basically, the processes act as if they are directly connected with each other. They don't have to worry about the fact that in reality, there are many routers and link technologies interconnecting the hosts on which these processes are running. So this is kind of shown in this figure. So to the application process, this appears as a logical connection. But the path taken by the actual messages goes in this particular fashion to reach the other process. In providing logical communication, an important aspect to address is the multiplexing, demultiplexing of packets, that is delivering the packets to the right process. We touched upon this when we were covering the interlayer communication. So that's something the transport layer has to provide. In addition, the transport layer can enhance the network layer service. More on this shortly. The transport protocols are also called end-to-end protocols, since these are often implemented on the end hosts. So this is again captured here. So as you can see, they are implemented only on the end host and not in this intermediate routers. Again, a terminology issue. Henceforth, we will refer to a unit of data at the transport layer as a segment. So if you see in this figure, the transport layer is between the application layer and the network layer. It provides service to the application layer, and it itself takes service from the network layer. So to understand the role of the transport layer, it is useful to understand what the application requirements are and what kind of service the network layer provides. If you are an application developer writing code for, say, an email application or a file transfer application, as part of these applications, messages have to be delivered. How would you like these messages to be handled? So for example, I would like guaranteed delivery of messages, because I wouldn't like some portions of my email to be lost. The same applies for file transfer also. Can you think of two other application layer expectations? We touched upon this before. Depending on the type of the application, applications typically have certain expectations. So applications like email, file transfer, web browsing, many of these applications like guaranteed message delivery. They also like order delivery. Real-time applications expect delay guarantees. And again, you don't want any duplication to be done to your messages. Some applications would like support for arbitrarily large messages. In other words, would you like it if someone said keep your emails to under 5000 bytes? So applications like file transfer or email, you want to support arbitrarily large messages. Some applications may also want flow control. What do I mean by this is keeping track of the buffer space at the receiver so that the sending application doesn't overwhelm the receiver buffer space, thereby leading to loss of data. So these are application layer expectations, and then there is the network layer limitations. We have already seen that the IP layer provides best effort service. What can it do to packets sent to it? We have covered this before. Name at least 2 things it can do. Well, it can lose packets, it can reorder packets, it can duplicate packets, and it can also place certain restrictions on the message size. This arises from the MTU, which we have discussed before, and it can also delay the packets. As you can see, the expectations are totally contradictory to what the network layer can provide. So how should one meet the application layer expectations? One approach could be to tell the application, fine, this is the network layer service. If you want anything else, you build it yourself. But if many applications want the same kind of service, for example, this guaranteed message delivery is needed by many applications, email, file transfer, web browsing, so on and so forth, in which case it may be useful to implement this service as part of the communication infrastructure itself. So that's where the transport layer comes into play. The challenge at the transport layer is to enhance the network layer services to meet the application layer expectations. Note that you cannot provide services as part of the transport layer that inherently cannot be supported by the network layer. For example, the underlying networks do not support delay guarantees, then there is no way you can support delay guarantees as part of the transport layer. But some of these other features like reliable transport or duplicate packet suppression or in-order delivery can potentially be supported. So we have different transport protocols that offer different trade-offs, that is, they meet different application layer requirements. Note that unlike in IP, where there was a common protocol at the transport layer, we can support multiple protocols. User Datagram protocol is a very simple transport protocol. We will cover more of it shortly. Again, Transmission Control Protocol TCP is another transport protocol that provides reliable transfer, in-order delivery, so on and so forth. We will again look at it in more detail later. Remote procedure call is a transport mechanism that is used in distributed systems. As the name suggests, this refers to remote procedure calls. For example, when you're writing a program, you call certain procedures or functions, but often they are implemented as part of your own program. But if you want to implement certain procedures in some remote host, you need this particular mechanism. So as I said, this applies in distributed systems. And again, to cater to real-time applications, there is a real-time transport protocol. One point I should mention here is that for RPC as well as RTP, these both are developed over the UDP protocol. So some don't view these as protocols at the transport layer, they view this as protocols at the application layer, but that is not quite true because the mechanism that they are providing is logical communication between processes, which falls under the transport layer. We are anyway not going to cover these as part of this course. We'll focus only on UDP and TCP. A good time to break. Up ahead, we will look at multiplexing, demultiplexing, which is fundamental to any transport protocol.